Okay, let's discuss a very explicit example of a group homomorphism. Okay, so so let me just review the definition of the group homomorphism. The map F from, say, A to B, where A and B are groups, is a group homomorphism if for all A1 and say A2 in the first group, the map of A1 composed with the map with the image, of A1 composed with the image of A2, and this composition is in the second group, so the multiplication law is the second law, second in the B group, is equal to the image of A1 and A2, the multiplication of A1 and A2 in the first group, right? If this is satisfied, then we say that this map is a group homomorphism, right? So another way of saying is that a group homomorphism is a homomorphism that preserves the group structure. Okay. So I wanted you to prove the following theorems or lemmas. And you should do it if you're maybe in the next class or the class after, we can just like discuss this if people are didn't have issues. So number one is that, actually, no, sorry. Let me make some comments about homomorphisms in general, okay? So a homomorphism is known as 1-to-1 if, say, for each A in the first group, F maps it to a unique element in B. What do I mean by that? Like if, say, A1 and A2 are different elements in the first group, then F of A1 is not equal to F of A2, okay? So if that is the case, then we say the map is 1-to-1. Okay, so let me draw a picture, since you guys like pictures so much, what I mean. So suppose we have a group A, another group B, and I take some random element, say A1, another element A2, and I map A to B. So this is A and this is B. So this map takes A1 to some element B1, and the same map takes, A2 to some other element B2, okay? So B1 and B2 are different. Now, there is no requirement for this map to actually cover the whole of B, okay? For this to be 1-to-1, it can be that, the first group A if the image of A is a subset of B, that has nothing to do with one-to-one. Okay, that's actually irrelevant. It can be, but it's not needed. Right? So there could be elements in B that this map, none of the elements in A map to this part of B. Okay, we don't care about that. So such a homomorphism is called one-to-one, and I think it's also called an injection. Correct me if I'm wrong. Otun, are you there?
Yes, sir.
Is that's an injection, right?
Yeah. So injective map basically means one-to-one, and surjective means onto.
Yeah. Okay. So next we are going to talk about onto. Yeah. So this is one type of homomorphism. The other homomorphism is that a homomorphism. My A's all looks, yeah. A homomorphism is, so this is also called an injective map. Okay, is one-to-one, or say injective. But a homomorphism is onto or surjective, right? If the image of F is the full set B. Okay. So that's basically what it means by. So if I draw a picture, so this is say A, and this is B, and what is saying is that you start from, you have a map, and from A, and it covers all of B. Okay. Sorry. So the way I want to, mathematically, the way to express this is to say that, for all B elements in B, there exists some A in the first group A, first set A, such that, so these are not groups, these are sets, because we're just talking about maps. We're not talking about groups in particular. So that such that F of A gives me B. Okay, so for all B in B. If that's the case, then it's an onto map. It's also known as a surjection. Okay. And number three is that if a map is one-to-one and onto, then the map is called a reversible map or a bijection. Basically, what happens is that, when a map, if F is say onto and one-to-one, then F inverse exists. Okay, and sorry, it's reversal, but it's called an isomorphism. Sorry. Okay, is Is it also known as a bijection, Apurna?
In general, is it called bijection? And if that map happens to be a homomorphism and a bijection, then we call it a isomorphism.
Oh, okay. So this is not a bijection. So this is just a homomorphism, isomorphism, right?
Yeah, bijection is the general term, and if it's a
Oh,
bijective homomorphism, then we call it isomorphism.
okay. So yeah. So this is basically an isomorphism. So basically, the isomorphism means that, you know, if you have a map, then F inverse exists, right? Because then what happens is that, you know, you've got two sets, A and B, and every element in A has a unique element in B, right? And in such a way that no element in B is left behind. So if you take any element in B, there is an associate element in A. So, you know, so essentially that correspondent gives you the F inverse, okay? So if it's a one-to-one and onto map, then finding the inverse is trivial. Okay, can someone give me an example of a function which is not one-to-one or not onto?
Sin x is not one-to-one. Like
Sin x is, what is the domain and the range?
like take the whole real line, then it's not
All right, so
one-to-one.
right, so for different values of x, we get the same values of y, right? Yeah. And any other examples?
X squared.
X squared, very good. Because, you know, if I have 4, then x can be plus minus 2, right? So yeah, we know these things, functions, and we just we are not, you know, we don't think of functions as maps, but that's what they are, right? So let's look at example of a map that is, you know, from group theory, okay? A very simple example.